Welcome to Makaut Smashers. Today we are diving into the mind-blending world of quantum computing, a revolutionary field that promises to reshape the landscape of computation as we know it. In classical computing, the foundation of our digital world, information is processed using bits, which exist in one or one of two states, 0 or 1. It is a binary dance that has powered our computers for decades. But what if we told you there is a new player in town, a computing paradigm that defeats the limits of classical physics? Enter the quantum computing. Unlike classical bits, here is quantum bits or qubits can exist in multiple states simultaneously. So how quantum computing differs from the computers we use every day? It's not just about speed, it's about leveraging the weird and wonderful principles of quantum mechanics to perform computations in a fundamentally different way. As we journey through this video, we will explore the basics of quantum mechanics, understand the key principles that make quantum computing possible, and unravel the potential applications that could transform industries. Buckle up, and because the quantum revolution is underway and we are about to embark on a journey into quantum realm, let's explore the incredible world of quantum computing together. The first part, we discuss about the historical overview. So, at first, the birth of quantum computing, 1980. Our story begins in 1980s with pioneers like David Eustace and Richard Feynman laying the theoretical groundwork. Feynman proposed the idea using quantum systems to simulate physical processes, showing the seeds for what would become quantum computing. The second is the quantum bits and algorithm, 1990s. In 1984, Peter Shor and Love Grover changed the game. Shor devised an algorithm that could factor large number exponentially faster than classical methods, posing a potential threat to classical encryption. Grover, on the other hand, unveiled an algorithm that could search unsorted databases quadratically faster than classical algorithms. The second is, and the third point, theoretical foundation, 2000. The early 2000s saw the theoretical underpinning solidify. Concepts like quantum entanglement, superposition, and quantum gates become integral to understanding of quantum computing. Scientists began exploring how to harness these principles for practical computations. Experimental milestones, mid-2000 to 2010. The transition from theory to reality gained momentum. In the mid-2000s, small-scale quantum computations were achieved in labs. IBM, for instance, demonstrated simple quantum algorithms using a handful of qubits. This period laid the groundwork for the development of various quantum technologies. Number 5. D-Wave and quantum annealing, 2010. In 2011, D-Wave systems claimed to have built the world's first commercially available quantum computer. Although debated for its true quantum nature, D-Wave's quantum annealing approach offered a different perspective of quantum computing, focusing on optimization problems. Number 6. Quantum Supremacy, 2019. A milestone moment arrived in 2019 when Google claimed to achieve quantum supremacy. Their 53-qubit processor, Sycamore, reportedly performed tasks faster than the most powerful classical supercomputers, demonstrating the potential superiority of quantum computation in certain scenarios. And the quantum race, 2020. Today, the major players like IBM, Microsoft, Google, and the startup are engaged in a fierce quantum race. Quantum computers with increasing qubit counts are under development, with a focus on addressing challenges like error correction and scalability. As we journey through historical landscape of quantum computing, it's evident that what started as theoretical musing has evolved into a dynamic field with the potential to revolutionize how we process information. We should need to learn about some fundamental or the basic principle of quantum mechanics. At first, superposition. Imagine a classical bit as a coin that can be in one of two states, either heads or tails. Now, either in quantum realm. In quantum mechanics, particles like electron can exist in multiple states simultaneously. This phenomenon is known as the superposition. A quantum bit or qubit can be in a state like 0, 1 or any combination of both 0 and 1 at the same time. It is as if our quantum coin is spinning in the air, showing both heads and tails until we measure it, right? So, the second is entanglement. What is this? Entanglement is a phenomenon where two or more particles becoming correlated to the extent that the state of one particle instantaneously influences the state of another, regardlessly of the distance between them. It's like having two quantum coins that once entangled always land on the same side, even if they are light years apart. This interconnectedness allows for the creation of qubit pairs with a unique relationship, a property harnessed in quantum computing for various applications. Number 3. The quantum gates. Classical computer processors information using logical gates like AND, OR and NOT. Quantum computers, however, leverage quantum gates to manipulate qubits. These gates perform operations like exploit the principles of superposition and entanglement. Quantum gates enable the creation of complex quantum circuits, allowing for the execution of quantum algorithms. The common quantum gates include the Hadamard gate, C-NOT gate, controlled NOT, and others, each serving a specific purpose in quantum computation. The qubit and classical bit. Classical computers like bits and which can be in one of two states like 0 and 1. They process information sequentially, like flipping through pages of a book. Quantum computers powered by qubits operate in an entirely different manner. Qubits can exist in superposition, allowing them to represent both 0 and 1 simultaneously. This parallelism grants quantum computers a unique computational advantage. Additionally, qubits can be entangled, creating interconnected states that classical bits cannot emulate. There are various types of algorithms in quantum computing, like Shor's algorithm for factorizations, Grover's algorithm for search, quantum Fourier transformations, and quantum approximate optimization algorithm. So at first we discuss about the Shor's algorithm for factorization. Imagine trying to factorize a large number into its prime components using a classical computer. These tasks become exponentially more challenging as the number grows. Enter Shor's algorithm, a quantum algorithm devised by mathematician Peter Shor. This algorithm has the remarkable ability to factorize large number exponentially faster than the best known classical algorithms. The significance: Shor's algorithm poses a potential threat to widely used cryptographic systems based on the difficulty of factoring large numbers. If fully realized, it could revolutionize the field of cryptography and digital security. Second, Grover's algorithm for search. See, searching through an unsorted database is like looking for a needle in a high stack. And classical algorithms do this by checking one item at a time. Grover's algorithm, designed by law of Grover, takes a quantum leap in search efficiency. It can search an unsorted database quadratically faster than the best classical algorithms. The significance of Grover's algorithm lies in its potential to speed up tasks like database searches and optimization problems, impacting fields ranging from data retrieval to combinatorial optimization. Like, third is quantum Fourier transformation, or QFT. The quantum Fourier transformation is a fundamental building block for several quantum algorithms, including Shor's algorithm. It efficiently transforms the quantum states of a system, allowing quantum computers to process information in ways that classical computers cannot. QFT plays a crucial role in quantum phase estimation and quantum signal processing. Number 4 is about quantum approximation algorithm, or QAOA. QAOA is an algorithm designed for solving optimization problems, a class of problems pervasive in various industries from finance to logistics. It leverages quantum parallelism to explore multiple solutions simultaneously. potentially providing speed up in finding optimal or nearest optimal solutions compared to classical optimization algorithms. Another topic is about quantum hardware. So, superconducting qubits, IBM, Google. Superconducting qubits are at the forefront of quantum computing efforts by companies like IBM and Google. These qubits operate in a superconducting state, allowing electrical current to flow with zero resistance. Superconducting circuits form the basis of these qubits, and they are manipulated using microwave pulses. The challenges like maintaining coherences and minimizing errors. Google's CMOR processor, a notable example, has been at the center of claims for achieving quantum supremacy. The trapped ions. Second, IonQ. IonQ and other companies employ trapped ions as their qubit technology. In this approach, individual ions are trapped and manipulated using electromagnetic fields. Qubits are represented by the internal energy levels of these trapped ions. Trapped ions offer relatively long coherence times, a crucial factor for error detection. IonQ's focus on trapped ions showcase the potential for scalability and error mitigation in quantum computing. Number 3. Topological qubits. Topological qubits are a theoretical and experimental approach that utilizes ions, anions, exotic particles with non-trivial braiding properties. The braiding properties of an anion is used to perform quantum operations. Microsoft has been a notable player in the pursuit of topological qubits through its Station Q project. The topological approach aims to create inheritance error resistance qubits, known as topological qubits, by leveraging the unique properties of anions. Quantum dots. Quantum dots are semiconductor-based artificial atoms. In quantum computing, they can be used to trap electrons, serving as qubits. The quantum properties of these dots can be manipulated to perform quantum operations. Quantum dots are particularly interesting for their potential in creating scalable and manufacturable quantum processors. Various research institutions and companies are exploring quantum dots for quantum computing applications. Okay, number 5th topic is about photonic quantum computing. Photonic quantum computing leverages photons, particles of light as qubits. Photons can be manipulated using linear optical elements and detectors to perform quantum operations. This approach holds promise for creating scalable and fault-tolerant quantum computers. Companies like Exenedu Quantum Technologies are actively working on developing photonic quantum processors. Some challenges in quantum computing: decoherence and noise, error correction, scalability, maintaining quantum states means quantum coherences. At first, decoherence and noise. Quantum systems are highly susceptible to interface or interference from their surrounding environment, a phenomenon known as decoherence. External factors such as temperature fluctuations and electromagnetic radiations can disrupt the delicate quantum states of qubits, leading to errors in quantum computation. Quantum coherences is fragile, and maintaining it in the presence of external influences or noise is a formidable challenge that researchers and engineers grapple with. Strategies such as error mitigation and fault-tolerant quantum error correction codes are being explored to address these issues. Some error correction. Error correction in quantum computing is an intricate challenge. Classical computers use redundancy to correct errors, but quantum errors correction involves more complex techniques due to the unique properties of quantum systems. Implementing error correction codes such as the surface code introduces additional qubits dedicated to error detection or correction. However, this time at the cost of increased qubit requirements and the need for fault-tolerant quantum gates. Overcoming these challenges is essential for building practical and scalable quantum computers. Scalability. Building large-scale quantum computers with a high number of qubits is a formidable task as quantum computers grow in size. Maintaining coherence and preventing errors become increasingly challenging. The complexity of scalable or scaling quantum processors without compromising performance or introducing more errors is a crucial hurdle. Researchers are exploring various quantum architectures and materials to enhance scalability and pave the way for the development of quantum computers with hundreds or even thousands of qubits. Maintaining quantum states or quantum coherence. Quantum coherence refers to the ability of qubits to exist in multiple states simultaneously, a feature essential for quantum parallelism. However, maintaining coherence over extended periods, known as coherence time, is a significant challenge. External factors such as interaction with nearby qubits or the environment can disturb coherence. Techniques like quantum error correction, dynamic decoupling, and advanced qubit designs are explored to extend coherence time, but achieving coherence times sufficient for practical computation remain a critical challenge. Okay, so next topic is about quantum supremacy and current achievements. Quantum supremacy defined. The quantum supremacy is a milestone in quantum computing where a quantum device performs a specific task more efficiently than the best classical supercomputers. It is a demonstration that a quantum computer can solve a problem that is practically impossible or extremely time-consuming for classical computers. Quantum supremacy showcases the unique computational power of quantum machines in certain domains. Next is Google's claim with the Makaut processor. In October 2019, Google made a groundbreaking announcement claiming to achieve quantum supremacy using its 53-qubit quantum processor, Makaut. The achievement was published in the scientific journal Nature in the paper titled Quantum Supremacy using a programmable superconducting processor. Key aspects of Google claim: task complexity, Makaut's performance, and controversies and debates. Significance of quantum supremacy. Quantum supremacy is a watershed moment in the development of quantum computing. It signals that quantum machines have the capability to outperform classical computers in a specific task, even if those tasks might not have immediate practical application. Achieving quantum supremacy does not mean that quantum computers can solve all problems faster, but it does showcase their potential for certain types of computations. Some current and ongoing research achievements, like since Google's announcement and other companies and research institutions have made strides in quantum computing. IBM, for instance, has continued to advance in its quantum processors, and startups like Digit Computing and IonQ have made notable progress. Okay, researchers are exploring new algorithms and error correction techniques to make quantum computers more practical for a wider range of applications. Next is about the quantum applications. Cryptography. Breaking secure codes. Quantum computers, particularly through algorithms like Shor's algorithm, have the potential to break widely used cryptographic schemas such as RSA and ECC. The ability to factor large numbers exponentially faster than the classical computers could render existing encryption methods vulnerable and necessitating the development of quantum resistant cryptographic algorithms, creating secure codes. On the flip side, quantum computing can contribute to development of quantum resistant cryptographic protocols. Post-quantum cryptography aims to create encryption methods that remain secure even in the face of quantum attacks. Quantum key distribution (QKD) is one such area, utilizing the principles of quantum mechanics to secure communication channels. Optimization problems. Quantum computers excel at solving complex optimization problems, a category with applications with various fields like logistics, finance, logistics, optimization routes for delivery trucks, finding the most efficient supply chain configuration, and solving traveling salesman problems can be significantly accelerated with quantum algorithms like quantum approximation optimization algorithm QAOA. Finance, portfolio optimization, risk analysis, and option pricing in finance involve intricate optimization problems. Quantum computers could provide faster and more accurate solutions, impacting decision-making processes in the financial sector, and also drug discovery and material science and machine learning and AI. Quantum computers have the potential to enhance machine learning algorithms, could outperform classical counterparts in tasks such as pattern recognition and optimization. In neural networks could be used and simulate and optimize the neural networks, potentially leading to advancement in AI. Challenges and fraud detections. While these applications hold great promises, it's important to note that the practical and scalable quantum computers capable of outperforming classical computers in these areas are still in the early stages for development. Overcoming challenges such as error correction, decoherence, and scalability is essential. Quantum hardware continues to advance, and researchers refine quantum algorithms and error correction techniques. The transformative impact of quantum computing on this application is expected to grow exponentially. So some future outlook is increasing qubit count, error correction advance, hybrid quantum classical systems, algorithmic advances, and commercialization and industry adoption, global collaborations. Okay, and in conclusions, I suggest that in this journey through the quantum landscape, we have explored the fundamental concepts of quantum computing, from the principles of superposition and entanglement to the various quantum computing technologies employed by the industry leaders. We have delved into the key quantum algorithms and applications across diverse fields. Okay, so to stay abreast of the latest development in quantum computing, I encourage you to explore the further resources, stay curious, and dive deeper into this fascinating field. Read articles, follow research publications, and engage with the vibrant quantum community. The journey into the quantum realm is dynamic and ever evolving, and your curiosity can be the catalyst for your understanding the quantum future. Thanks for watching, and like, share, subscribe our channels for more videos. Okay.